Well, thank you, Tyler, and welcome everyone for this session. And we would love to share some of our use case and experience with StarRocks with you guys. And hopefully, there will be something as a good takeaway, and you can apply to yours. And I would like to get some ideas from you as well. And we want to learn from each other in this StarRocks stage and the form today. All right. Let me just give a heads up about what we're gonna talk about in our session. We want to review a little bit of where we came from and how do we end up trying and using and depending on StarRocks. And then we will talk about a couple of use case focused on blockchain, and then some of the enhancement that we closely collaborated with StarRocks together and contribute back to the community and to improve the overall reliability and throughput. And we're going to share a little bit, comparison between ClickHouse and the StarRocks with our recent benchmark, exercise and see and why we see certain things and how we mitigate the different, strengths and weakness of that. And talking a little bit about some of the challenges we're facing. And before we close up, we would like to share some of the data modeling, query tuning, and design principle that we found even on top of the very powerful StarRocks system. And we find some of the things maybe the AI models doesn't know as of today. We would like to share that human intelligence and with everybody. And then we're going to close with a little bit what's working in progress and with us. All right. So let me have a little bit of reflection about our journey with StarRocks, right? We have to really talk about the nature of crypto data. Crypto data started around maybe 2010, right? Maybe it's earlier, but then really came to the public around 2010, 2012, that time. And then the data volume really exploded after 2017. And then in 2021 to 2025, the data volume probably continued to increase at a astronomical rate. So we have over probably 3 billion 30 billion transactions happening on Ethereum, and 100 times more on BTC, and 1,000 times more or 10,000 times more on Solana already. So because the blockchain data is very open and the analytical appetite for blockchain is very, very big, and we're looking for some system can balance both the fast data ingestion, join capability, but also near real-time data serving for us. That's why around the 2021, 2022, we were looking for different candidates in the market, and we tried a few things, including TiDB, and then StarRocks, and we built some strong use case around StarRocks, and we have a close partnership with them. And even though at the time, and the Coinbase also have some others, teams are also using ClickHouse, and this is still the case today. And we're doing some comparison between them and trying to find the best use case to use StarRocks, right? And today, and my coworker Xinyu is going to share some of the flagship use case that we use a lot of data, has very tight latency requirements with blockchain data based on StarRocks. And so Xinyu, why don't you just tell us a little bit more about those critical use case?
Thank you, Eric. The first blockchain use case powered by StarRocks is our Blockchain Transaction Explorer. It is a UI tool, helps analysts detect suspicious activities across multiple blockchains, protecting customers and ensuring regulatory compliance. Starting from a blockchain address, analysts can quickly search and view transactions to or from that particular address. The Explorer generates summaries and highlights potential suspicious activities linking to drug trafficking, terrorism, scams, or sanctioned entities. It automatically assesses risk levels and apply labels to the transactions associated with each address. Today, this Explorer supports 10 blockchains with over 300 tables and 573 billion rows of data stored in StarRocks. The second use case is Tracer. Tracer service helps analysts uncover illegal activities by tracing the flow of funds back to its source, revealing a fake ID vendor ring as shown in the graph on the right. So it is powered by Puppy Graph, a graph data warehouse for graph analysis, and StarRocks for data storage and query execution across blockchains. Together, they power a visual interface that enables analysts to follow money trails with speed and clarity. Let's quickly look into the architecture for both the Blockchain Explorer and Tracer. Databricks or Spark handles large-scale data processing with results stored in data tables. StarRocks synchronizes with those data tables every 12 hours. Besides, asynchronous materialized views are created for additional aggregations. This ensures analytics queries return in just a few seconds. To improve freshness further, the Tracer team is moving from periodic ETLs to incremental ingestion, streaming change data feed CDF events, or named as table change events from Databricks directly into StarRocks via the Spark connector. StarRocks and Kafka together powers real-time analytic queries. Do you need both strict data freshness and low latency queries? That's where StarRocks combined with Kafka really shines. StarRocks provides an open source Kafka Sync connector. Our Coinbase data platform team partnered with CelerData engineers to fix bugs and optimize this Kafka connector. The result: sustained ingestion throughput of 30,000 Kafka messages per second into a primary key table. It is worth mentioning that absurd operations to a primary key table are more expensive than append-only writes to a duplicate key table. Depending on the throughput, freshness lag typically ranges from a couple seconds up to a couple minutes due to heavy data buffering and batching configured on the Kafka Sync connector. Note, StarRocks also offer routine load, where you can configure a load job within StarRocks to pull data from a Kafka cluster. Between the Kafka Sync connector and the routine load, we prefer the connector approach because it offers rich data format support, including JSON, CSV, protobuf, Avro, and more. It also has built-in data transformation through the Kafka Connect SMT. It offers strong observability through the connector building metrics. We use this approach to ingest both front-end events generated from user clicks and backend events generated by backend services at real time to StarRocks tables, supporting various low latency analytic queries. At Coinbase, as Eric already mentioned, both StarRocks and ClickHouse are in use. We found that they share very similar several architecture similarities. Both are MPP systems, use columnar storage, supporting SQL, and provide materialized views. As a result, they fit similar usage scenarios, integrating with tools like Kafka, Spark, and Flink for analytics on CDC data, metrics, logs, and event streams. This naturally led us to conduct a benchmarking comparison between the two. We ran a TPCH 1 TB benchmark to compare them. For people who are unfamiliar with TPCH, it's a widely used benchmark to measure the performance of analytic databases and query engines. Both StarRocks and ClickHouse were deployed on AWS EKS Kubernetes with identical hardware and software setups, as shown in these two tables. And the test data set include 8 tables and 22 queries. Here we listed the 8 tables with different sizes on the right. Here's what we found. ClickHouse failed to complete 12 out of the 22 queries due to out-of-memory errors. On this chart, StarRocks results are in blue and ClickHouse in red. You can see that in many cases, the red bars representing the ClickHouse query execution time are simply missing. For queries ClickHouse did finish, StarRocks was constantly faster. ClickHouse performed especially poorly on queries involving joins. Here's the takeaway. StarRocks outperforms ClickHouse across all 22 queries from P50 to P99 latency. We hope these benchmarking results offer useful insights for others facing similar requirements and decisions. To share some of the challenges we have encountered, many backend engineers with limited SQL data warehouse experience underestimated the importance of the create table DDL to query performance. They assumed that warehouse would handle most optimizations automatically or magically, but later found themselves struggling to tune their queries. When the table schema is suboptimal, it often results in full table scans, heavy file I/O, and a long query execution time, or even timeouts. The typical first reaction to these issues is to request more resources, like adding extra CPUs or memory for the StarRocks cluster. There's a learning curve in mastering techniques such as selecting the right partition strategy, choosing partitioning and bucketing columns, defining primary key or sort keys, and leveraging asynchronous materialized views for pre-aggregation. Here we have really appreciated the CelerData support team, who have been very generous in helping our engineers optimize their query table SQL. Looking ahead, LLM-based AI agent can help reduce the demand for constant interventions from experienced engineers. In fact, StarRocks already provided an AI agent that assists with DDL optimizations. Now, Eric will walk us through some best practices for StarRocks using real-world examples. Eric, please take over.
All right, thanks for Xinyu, talking about the use case. And I'm pretty sure for all the sessions today, you're going to hear a lot of awesome thing about how powerful StarRocks it is, and for real-time analytics and fast ingestion, et cetera, right? But I want to just share a little bit anecdotal here. Is like, even for a powerful system like StarRocks, sometimes you can still get some problem there. And for example, I would like to spend a few minutes to explain a very, straightforward structure, right? This is the blockchain transaction history, right? For each transaction, you have a from address, and have a to address, you have some timestamp, then you have a lot of like a money status. This is a simple transaction records, but then this could scale up to like 3 billion, 30 billion, 100 billion, or maybe trillion records. It is the problem when this table is so big, and we are going to face a lot of scaling issue. And that's why we need to revisit the data modeling and the query pattern and see what can we do better to make the most out of the StarRocks. I really try to avoid people try to abusing StarRocks just because it was powerful. Let's just dump all this kind of queries into StarRocks and expect it will work well. So without going into too much detail, I would like to invite you to take a look at the query at the bottom, the select query, which is pretty simple, right? We just try to see if I have a particular wallet address. I want to find its recent transaction so that I can display this on my UI for people to explore. this is a very typical business use case. And I personally feel like this query is very simple, straightforward. There's nothing we can change about it, right? But it is this actual simple query that can cause a lot of frustration for the application team, right? So number one is when you run this query with, let's say, only 1 month worth of data, you don't see any problem, right? This will be a pretty slow query in Postgres or something, but in StarRocks or even ClickHouse, this was like just like this, right? It's done very quickly. But then once you build your application, which have like concurrently 20 people are doing the data exploration, and they're just randomly put some address here, try to figure it out where to start to investigate about the activity of this address, they could have like 50 to 60 concurrent queries going against your StarRocks, and suddenly you can notice that the StarRocks becomes busy and this query will just be queued. This is very strange because this query is so simple and why, right? This one will slow down. And then the second thing I want you to pay attention is we want to talk a little bit about this later is the distributed by hash in the table definition here. And what we see here is the distributed by include both the to address and the from address. And then when you look at the query pattern is they're either looking for the from address match the value or the to address match the value. And this is another problem. When we design the distribution of the key, which is a very important feature of both ClickHouse and the StarRocks, and in this particular use case, we have two columns that potentially can be included in your predicates. How do we design this one? Should we distribute it by both? Should we distribute it by only one? How do we balance the query performance and the data distribution, right? Okay, so next slides, please. So the previous query has a problem is because it has to scan the entire history of the data and then sort the data and find the most recent one. If you're doing this one with like 3 or 5 concurrent query, you're totally fine. You don't see any latency increasement. But then when you have like a 30 or 50 queries are doing the same thing and doing the full table scan, and you're going to see the degradation of your system, right? Even with the StarRocks. So that's why your data model really matters. And the first thing we are going to do is to really align our table structure with your mostly used query patterns together to optimize that. And we need to reduce the excessive table scan in this case. Okay, again, let me emphasize, even with StarRocks, you do not want to do full table scan. Okay, if somebody tell you if you use StarRocks or ClickHouse, you will never worry about a full table scan again, I think that advice is very ill. Don't follow that. Okay, so now how do we do that? People, the query want to find the most recent activity of a given address. Either that address is a from or is to. So now the first thing is we need to really use the divide and conquer approach to mitigate this problem instead of using a brute force. And we have two options here. On the top, we want to partition the table really by the address so that it's okay, from the same address, it always goes to the same partition so that the filter will be pretty effective. But now the question is, remember the predicate is from address equals to something or to address equals something. When we look at the first table, how that will address the to, right? It won't be able to. You have to rely on the bitmap index. And then you're going to create a lot of data retention and a scaling issue here because all the address, the data will go to the from address. And then the other one is we need to look at the cardinality of the address, because we actually have over 300 million distinct address for the, let's say, for example, for Ethereum. For Bitcoin, your unique address is even more than this one. So that means, how do you actually partition by range on a such high cardinality column, right? This is not time. It is possible. You can use a prefix, you can do something, but it becomes very cumbersome to do that. So it's operationally not scalable, and the data retentionally not wise to do so. So that's why our practice is really say, you will continue to partition the data by the blockchain timestamp, and giving them a monthly partition at the top level. And then you can only distribute your data by one of the address. You cannot do both. If you do both, and your query must use and instead of all in your predicates. But how many times you're going to see a query try to find a transaction with both the from address and the to address both known? You have that, but you don't have many, right? A lot of query will only have a rough idea about either from or to. So you can only optimize for one of them and leverage the index for the other one, right? That's a trade-off you have to do. And then the last one, you need to use the order by. So in this case, if we really distribute the data by from and order by the data also by the from address, then we can avoid creating the bitmap index from the from. So we only created index from the for the to address. So that is one of the trade-off we can do. Of course, we have the second option, which is a little bit more complicated, but which is also working. It's like you have a main table, which is optimized the from address, okay? But then you have the secondary table, which is a link table, which is optimized the to. And then you need to use the second table to do the filter and find the unique key, which is typically the transaction ID or the from address plus the timestamp and plus the block hash. Then you can use that compound key to join back to the first table. StarRocks is very good to do the join using the primary key or the unique key, right? You can take advantage of that. Right? This is a really complicated thing, but then trust me, it's worth the effort, right? Okay, but now let's go back to the simple solution first and see how we can do this even better. You need to do a pre-aggregate table at the monthly level. So for every month, you can build the materialized view at the address level for both from and the to. Then you can pre-aggregate everything to say, in this month, for this particular address as from, how many times they have appeared in the transaction. So among this 300 million address, you can see it's going to be sparsely populated. Not everybody, every wallet address will have transaction every month. I would argue probably 90% of them will not show up, okay, every month. So if you have this like a table, then you can actually query the aggregate table first and to see whether that particular address even appear in that month. Now you can imagine this kind of scan is very, very small, right? It's not going through the big, transaction detail, but this is another pruning technology you should use. All right. So I think we have a couple of minutes. So let's talk about the scatter.
Yeah, Eric, I appreciate we're running very close in this. The event actually is going to auto close in about a minute. So I just wanted to let you know ahead of time.
Sure. Yeah. So this is the idea, like say you can break this one using the pre-aggregate table and using the scatter and the gather pattern, which is more used in the search index kind of a capability to do. Instead of fire one big query to scan the entire table, you fire 3 tiny queries to scan small partitions. And then each one will run much faster and you will not impose a lot of overhead to the StarRocks system. That's why you shift your complexity to your application side to free up the capacity of StarRocks. Now you can serve 100 concurrent queries without sweating. That is the one example we want to really talk about today, and hopefully you will learn. Even with the powerful StarRocks, we need to do a better query planning and much better data modeling. All right, next one. Next one is really, we want to say, okay, we want to build this one with self-service capability so that we can integrate this with our self-service hub, so that we don't have to everybody be a codified hero to use StarRocks. We want everybody to use a UI to leverage, StarRocks, building a streaming pipeline, and handle the operation and the monitoring. Right, that's what we really care about, the overall DevX developer experience for StarRocks. Right. All right, I think that's pretty much what we want to share with all of you. And if you have any questions, now we're open for it.
Yeah, we've got about a couple of minutes left. I know, fortunately, Eric's been really great about answering questions in the chat while we've been going. There's only one question in the Q&A right now. Do you run shared data architecture, shared nothing? Do you test the other? Do you test the other / how much faster was it for those specific use cases?
Yeah, that's a question for Xinyu, I guess.
We run share nothing. We don't, at this moment, we haven't tried the share data in S3 yet.
Okay.
And what is the second question, sorry?
It was if you had tested that, and how much faster it was if you tested the other.
We haven't. We haven't compared the two yet.
Okay, no problem. Well, is there another question? Are you planning to move all transformations on StarRocks for data lineage?
We need a clarification about who asked the question? Like a data lineage can go across the system, right? You can do your transformation in Databricks and replicate the result to StarRocks, or you can do the pre-aggregation in StarRocks and using StarRocks as a source and propagate the result to Databricks. The lineage will be maintained by your lineage instrumentation system. The main thing is which system had the best capability to do the transformation. Because right now, StarRocks is still working on the right path, so that a lot of this transformation need to be done in Databricks or Flink, right? But once StarRocks becomes strong on the right, and I think more and more transformation can be moved to StarRocks, right? This is already happening in Presto, right? People think Presto can only be used for reporting, but now Facebook probably run 80% of their ELT in Presto already. So that's why, with the new capability, the lineage will actually shift. I don't know if that's the intention of the question, but I'm trying my best to answer it.
Well, that's great, and I know we're kind of up on time now, so I really appreciate both of you for coming. Thanks to everyone who joined us as well today for this session. Don't forget to complete the poll question on your way out, and please, scan the QR code on the screen if you haven't joined the StarRocks community yet. It's a great place to connect with folks, and I think if you have follow-up questions we weren't able to get to today, you can track Eric and Xinyu down. But the next session should be starting right about now. So, please head to your next sessions. But once again, thanks to both of you guys for coming today. This is a really fantastic presentation.
Thank you.
All right. Thank you very much.